Okay. Okay, so as already said, this is a joint work with my collaborator Birgit Roensch, also from Erlangen-Nürnberg. And the outline is the following. Should I be here or here? Okay. So I will show. Oh, sorry. I will show you a far-reaching and flexible toolbox of distances, divergences. We have already encountered many of them between two probability distributions G and F. And we apply this to the very important context of independent but non-homogeneous data. So we cover exponential families and also a very hot topic in artificial intelligence, namely the generalized linear models. Okay, and for those I give you estimates which are robust and therefore are alternatives to the well-known maximum likelihood methods. And at the end I will derive some asymptotic distributions for the new estimates. Okay, so many things have already been said, so I will save some time now by the nice talks of Frank and Michel. So divergences are very prominent in statistics, machine learning, artificial intelligence, information theory, etc., etc. And so as already mentioned, so the question is always how to measure the distance between two probability distributions. So we have seen already many examples. So for today we have two major classes. The one are the Chisa, Ali, Silvey, Morimoto divergences. And we have already seen that this covers the Hellinger distance, the Pearson's chi-square distance, the total variation distance, and many more. And it covers also the Kullback-Leibler or the relative entropy. The Kullback-Leibler is also a member of the second important family, basic family, namely the classical ordinary Bregman distances. Okay, and the L2 distance is another prominent member of that, and also the so-called density power divergences. We will see them later on. Okay, and of course, so at least we had the desire to have a whole toolbox, you know, of divergences or distances, okay? And the toolbox or the flexibility is reflected by the divergence generator phi we have already seen in Frank's talk, and I also use a scaling M, okay? So how does this work? So we are quite general, so we use a reference measure lambda, and with respect to this reference measure, so these two probability distributions should have a density, G and F, and the scaling also should have a density, I call it M, but the scaling need not be, and typically is not a probability measure, okay? But a non-negative measure, okay? So the special case, so if the reference measure is the Lebesgue measure, then everything, they are plain ordinary densities, okay? For M, they are not normalized, but here the total, mass is 1 for G and F. So just classical, think of Gaussian and maybe non-normalized Gaussians, okay? So, and the other important special case is if lambda is the counting measure, so we have maybe a discrete set of states, and for each state, lambda puts the mass 1. That's the counting measure, okay? And then G, F, and M are just classical mass functions or counting densities or frequencies, maybe non-normalized for M, okay? Just think of that, maybe Poissonian, binomial, things of that, okay? So all the important, and of course you can take mixtures thereof, yeah? So, and as already in Frank's talk, and also in the talk of Michel, we need a divergence generating function phi, which for today should be continuously differentiable, so we don't want to avoid these maybe practical problems here. They should be strictly convex, and we extend them on the boundary, but the boundary is 0 and infinity, so no negative densities here. So, and then Igor Weida and myself introduced the Bregman distance between the two probability distributions G and F, and they are scaled by typically a non-probability distribution M. And it looks like, so the basic body is related to what Frank already told us. The difference is that we scale G and F, we scale by the scaling density M here. And then after taking, you will see a picture in a moment, after taking the so to speak, the difference between the function and the tangent line, we rescale again by M, and then we sum up or aggregate by lambda, okay? So of course, you see if G and M and F have zeros, then one has to be a little bit careful of how to write things down, and there's a comprehensive studies of that in the recent paper with Michel in the recent new volume of the nice book of Frank on information geometry. Okay, well, these distances are really distances, okay, and if we have a discrete setup, okay, then the integral just turns into a sum, okay? And well, the picture you have seen with Frank, the difference now is that we don't take P and Q itself, but we rescale it. Then we take the tangent line, we take this distance here, and then we rescale it by M, and then we do it for each state, okay, and then we sum up, okay? That's the point. So also, now not in the context of the G-star divergences, but now in this context of scaled Bregman distances, we use the power functions. You see it basically, so alpha is here, the power here, and this is just some rescaling here, okay? And the case alpha to be 0 corresponds to the Kullback-Leibler, okay? And we also have the case -1, okay? Because otherwise we cannot divide here. Okay. So if alpha is larger than 0, there is no trouble with the zeros. If alpha is less than zeros, you have to include the zeros, and you can see it here. So if f is 0, you have to add up infinity, etc., etc. I don't want to go into the details here because mostly in the applications I show you, we don't allow for zeros. Okay, for today, yeah. Just to be more simple. So in here you see basically a Kullback-Leibler. Okay, if the densities are both larger than 0. Okay, you have Kullback-Leibler here. Okay. And here you have the reverse Kullback-Leibler without the zeros. Okay. So, yeah, that's already said. Yeah, and if alpha is taken to be larger than 0, and if the scaling is just 1, so it's unscaled, yeah? Remember, dividing by m now means dividing by 1, so everything is unscaled. Then these scaled Bregman power divergences are nothing else but the well-known density power divergences of Basu and collaborators of 1998. Okay, so Frank also already made our mouth watering that, of course, exponential families are very important for information theory, for geometry, for machine learning, artificial intelligence. And so also we used exponential families here even in a non-natural setup, okay, quite general, okay. So that means we consider families of P parametric exponential family, okay. So that means with the parameter theta, which may be a vector or something like that, then the densities should have this well-known form with the very important, of course, cumulant function P. This plays a decisive role here, P. Okay? So that's, you know, that. So I will show you a result where, you know, we want to measure the distance between two probability distributions, and this should come from the exponential family. And how about the scaling? The scaling has also an exponential form, but maybe of different form, and it need not be normalized, okay? Remember. So if we get this, you get an explicit formula for the distance between one family member and the other family member scaled by this other type exponential scaling, okay? I mean, I don't want to go through the formula. I just would like to show you that there is an explicit formula. And of course, alpha to be 0, remember, is the Kullback-Leibler case. And here it is, okay? The well-known result. Good. So, and you see here, of course, B, the cumulant generator plays a decisive role here, okay? Here, B, and the B tilde is the one for the scaling. Okay. So, of course, yeah. This generalizes an older result of Igor Weider and mine, where we have just natural family members. Okay, so that's not so important. And of course, as already mentioned, a typical case of exponential families is now in machine learning and also in earlier times, the generalized linear models. Okay, you can apply this. And there, the parameter, well, then you have independent data, but non-homogeneous data. Okay, so the parameters vary from time to time. Okay, but maybe are connected by some connector functions. Okay, that's a basic idea behind generalized linear models. Okay, so and this is a special case, and if there is no scaling, then things have been already done by Gauche and Basu a few years ago. Okay, so we extend these results. Okay, so now let's go back to the general case, again, and then we have, as you see here, the family of possible probability distributions of interest is of product form, reflecting then the independence, okay? But as you can see here, it's not the same f, it's a different f, okay? But connected by the same parameter, okay? So we also take alpha to be larger than -1 in order to avoid some troubles with the zeros, remember? Okay, so, and now we want to estimate, of course, the parameter out of data. But how do we do it? We take a minimum distance estimator, and the distance is the scaled Bregman distance, okay? So you see, you know, for each data point, remember, this is non-homogeneous, okay? We have a different G, so that's the true unknown data generating distribution, and this is the model family, okay? So, and we take the distance, and we sum up, and we average it, and we search for that parameter theta, which minimizes this aggregated divergence. Okay, and the corresponding, well, actually it's the functional, is our estimator. Okay? Of course, here G is still the true unknown generating distribution. Okay, so actually multivalued. Okay, but of course one wants to plug in data. Okay, so the G is replaced by a data-derived measure, by the corresponding one. So here, of course, we take, again, the Dirac functions on the data. Okay, we plug that in, and then we solve for the optimizing problem. Okay, and this turns out to be, some terms cancel out. And then after some manipulations, it turns out that the parameter we are searching for is the minimum of that guy. Depending, so if alpha is 0, look at this. This looks very familiar. Yes, that's the term to be minimized in the maximum likelihood case. Okay, but here we are more general. You see here, we are more general, and of course here the scaling plays a crucial role. Okay. So, yeah, as I said, see here. Alpha is 0. Remember, it's always Kullback-Leibler case. Relative entropy, that means maximum likelihood. And indeed, minimizing, leads to the estimating equation. So to be solved for theta, which is known as just the estimating equation of the maximum likelihood method. But in a more general case, alpha to be non-zero, you have to solve for this equation here. Okay? Good. And again, in the unscaled case, so if there's no scaling, m is identically 1, also not dependent on I, then this method was already done a few years ago by Gauche and Basu. And now we are more flexible. And in the other talk you will really see that for some problems, this method of flexibilizing by scaling is really superior to the unscaled method. Okay, so it's not just a game of generalization. It's really essential, at least for some cases. Okay, so at the end, I would like to show you asymptotic result for the estimators. For this, I need to introduce some notation which I will not go through. And here's the theorem. And there is the existence of the roots of the estimating equations. That's one important thing. And the other important thing is that the asymptotic distribution of the estimators with sample size n is approximately normal distributed. Okay? That's what you expect, but of course, the proof is quite lengthy, so it's not so obvious. Okay? Good. And so for this part, this is done. So let me recall. So I introduced you a far-reaching and flexible toolbox for measuring distances between the probability distributions. We applied it to independent but non-homogeneous data. And I gave you some robust alternatives to the maximum likelihood method. I did not talk about the robustness, but it will appear in the next talk. That it's known that the maximum likelihood method is not very robust against outlier contaminations. And you just believe me for the moment that our method is more robust. And I will show you in the next talk, in a concrete example, that this is really the case. And at the end, I derived you some asymptotic distributions of these new robust estimates. And here I would like to stop.
Thank you very much. Let's take this speaker. So are some questions?
That's good.
well, a novice's question. You look at the scale Bregman divergence, so you divide by n. Let's assume this n is strictly positive for simplicity.
Yes.
Isn't that the same as just multiplying the reference measure lambda by n? Where's the difference? If you go back to your slide.
No, it's a non-linear system. No?
If you go back to your slide where you introduce the scale
Yes.
divergence. Here,
Yes,
yeah.
we see here.
If I
But
multiply,
phi is a non-linear function. Think of squared.
that's fine, but if I multiply the measure lambda by the density m, I get a
Yes.
new measure, call it lambda tilde.
Yes.
And now if m is strictly positive, the measures corresponding to g and f will still be absolutely continuous with respect to this new measure lambda tilde.
Yeah, but it need not be a probability measure anymore. Right? Okay.
Of course. They still are probability. Oh, lambda is no longer a probability.
Yeah, okay. It's not.
And you
it's
require lambda to be
yeah.
a probability.
But it's a good point, you know, in the recent paper in Frank's book, we had a paper with, actually it's quite a comprehensive chapter. We discussed it on a more general level. It's a good point. So we use different scalings here for f and g, and we use a different aggregator here. So we have 3 scalings and discuss everything. But for today, I wanted to keep simple. But you can extend it also to this case. And then you recover, as a very special case, some newer divergences of Zographos and things like that who use similar methods.
Okay. Do we have more questions?
Yeah, I guess you already answered my question in your final one of your final comments.
Mm-hmm.
Yeah, my main question was actually, what is the advantage of introducing this scaling? Is it purely an empirical finding that you have more flexibility and hence it performs better? Or is there some, let's say, conceptual motivation?
It depends what kind of scaling you would like to have. Here I showed you, for instance, this exponential family scale. So this scaling here, I assume, I did not mention, but in order to keep things simple, m does not depend on f and g, but you can make it in an adaptive way. Okay? For instance, you can have m of x is the function h of p of x and q of x. Yeah? And then the question is how to choose h. And with a former collaborator, I had a very long paper in one of 2 or 3 years ago called statistical engineering and things like that. And then we really discussed how to choose h to get nice robustness properties on a very comprehensive scale. You may be interested. I'll send you the. So it really, there's much behind it.
Right. So thank you again for the very inspiring question.
Yeah.
I mean, I have maybe just maybe one kind of question.
Yes, sure.
What is the duality of the generator and scale Bregman?
No, not really to the full extent.
And I think also by putting this kind of scaling, you make it non-separable, right? If it's
Yes,
not uniform
yes,
distribution,
yeah,
and
sure.
somehow you can
Sure,
some
yes.
information
Yeah,
about
it's a
this.
non-trivial scale, of
Yeah,
course.
so basically you want to make a separable Bregman divergence non-separable.
In a sense, this happens.
Yeah.
But the first idea was also, you see, if I use this scaling, q of x, then as a special case, you have the Chisa, Ali, Silway, Morimoto divergences. And if you take mx to be 1, you have the ordinary Bregman distances.
Yeah.
So this covers both worlds which are typically completely different in one framework. That was one of the first motivations. But then, of course, these robustness studies, and there are very nice plots. You can, it's really, you can visualize it in a very nice way, different kind of robustness properties. You may look at this paper in 2006.
Okay, so now I think we are ready to listen to part 2, which is robust estimation with the extreme value scales.